This is Mr. Beck Does Your Homework. This is question number 1. It says a 20-kilogram bowling ball with a radius of 14 centimeters starts from rest at the top of an incline 3.3 meters in height. Find the translational speed of the bowling ball after it has rolled to the bottom of the incline. Assume the ball is a uniform solid sphere. That's going to be important. The acceleration of gravity is 9.81 meters per second squared. What might be helpful first is to draw a picture. We have a ramp, we have a bowling ball, and it is starting at a height which we're going to call h above the ground, or above the bottom of the incline. A couple things we know. We know the mass of the bowling ball is 20 kilograms. We know that the radius of the bowling ball is 14 centimeters, so that's going to be 0.14 meters. It says that the top of the incline is 3.3 meters in height. So my height is going to be 3.3 meters. And I'm looking for the speed at the bottom. Well, at the bottom, when the bowling ball gets to the bottom, it's going to be doing a couple things. It's going to be moving with a certain velocity this way, a translational speed. It's also going to be rotating with an angular speed. So I've got to take both of those into account. Now, if I'm talking about energy, I know that the amount of energy it has up top is going to be the same as the amount of energy it has in the bottom. So I'm going to ask the questions I usually ask with conservation of energy. First question, can it fall? Well, at the top, yes it can, so it's got some potential energy due to gravity at the top. Is it moving? No, it's not moving yet. It's being released from rest. So it's not moving, it doesn't have any kinetic energy. It's also not rotating, that's my next question. So it doesn't have any any kinetic energy due to the rotation. And there is nothing about springs in this problem. So really, all of my energy up top is going to be potential energy due to gravity. That is going to equal the amount of energy it has here at the bottom. So at the bottom, I'm going to ask, can it fall? And the answer is no. It's already at the bottom, so it can't go any further. So I'm going to say that it cannot fall, so I don't have any potential energy due to gravity. Is it moving? Yes, it is. So I'm going to have some kinetic energy, translational. Is it rotating? Yes, it is. So I'm going to have some kinetic energy due to the rotation. And then, again, there's no springs involved down at the bottom. So what I have is I have energy at the top equal to energy at the bottom. So now I can remember that my potential energy due to gravity is going to be my mass times the acceleration of gravity times the height. And that's going to equal my translational kinetic energy, which is 1/2 the mass times the velocity squared, plus my rotational kinetic energy, which is 1/2 the moment of inertia times the angular velocity squared. Since we're dealing with a solid sphere, that has a specific moment of inertia. The solid sphere has a moment of inertia of 2/5 times the mass times the radius squared. So 2/5 mr squared is going to be what I plug in here for the moment of inertia. And I've also got my omega. So if I rewrite this one more time, I'm going to have the mass times gravity times height equals 1/2 the mass times the velocity squared plus 1/2 of 2/5 times the mass times r squared times omega squared. Now, a couple things I'll notice. I will see that in this equation, there are a couple things that are going to cancel out. Actually, just one at this point. I can see that the mass is in every term, m, and m. Now, I have a GH, I have a V squared, and I have an R squared omega squared. If I'm going to try to solve for the velocity, then I'm going to have to do one more thing, and that is make sure that I can figure out what the velocity, what to do with the R squared and the omega squared. But if you remember, the velocity, V, does equal R omega. So V is going to equal R omega. That means that R squared omega squared is going to be V squared. So that will reduce to, again, let me write this what I know. I know GH equals 1/2 of V squared plus 1/2 of 2/5 times R squared omega squared, but that's going to be V squared. So now you can see, you can take it from here. You can plug in your gravity and your height. You have 1/2 of V squared plus another, let's see, 1/2 of 2/5. So that's going to be 2/10 of v squared, so 1/2 of v squared plus 2/10 of v squared. You can work it out and solve for v, plugging in, and you will wind up with a velocity that is less than it would have had if it was sliding down the slope, because now it's rolling down the slope, so some of the energy is contained in this rotational motion.